Good morning, everyone. Welcome to Chemistry with Professor John. All right. This is the continuation of stereochemistry in organic chemistry. All right. On the first part, we define stereoisomers. We define chirocarbons. Chirocarbons leads to chiral compounds. Okay. Now we're going to look at other examples. Now, if you have a chiral compound, okay, and if you build the molecule that's mirror image to it, like this one, you build a mirror image molecules, okay, and if they're non-stackable on the original one, then they are different, but they're mirror image to each other, okay. So we call them enantiomers, okay. They always come in pair, right? Okay, now in this part, we're going to be looking at different type of stereoisomers. We're talking about diastereomers. We're talking about mesocompound, okay? All right, now okay, let's take a look at this one. This two, okay, well, this molecule right here has internal plane of symmetry. So if you do the mirror image, okay, you can actually slide one over and they're the same, okay. So these are not enantiomer. And notice that although each carbon is chiral, this molecule has two chiral carbons, all right. We call this mesomolecules or compound. So mesocompound is a compound with chiral carbon, but overall not chiral, okay. So has chiral carbon, usually even number, but not chiral overall. Okay, that's mesocompound. All right, so that's definitely good to take note of. Okay, let's take a look at more example. These two, you cannot slide one over, enantiomers, okay. So this is molecule is chiral, okay, meaning it has a mirror image that's not stackable. Right? Not stackable. Chiral, there's no way you can move one over and stack them. Okay, now we do have compound that chiral, but that's no chiral compound without chiral carbon. Is that cool? Yep, these are ring structure. There's none of the carbon in here that's qualified to be chiral. They don't have 4 branches or atoms bonded to them. Okay, remember chiral carbon is the one with 4 different, bonded to 4 different atoms or branches. Okay, now here's another example but they fit definitions. They have mirror image that's non-stackable or non-superimposable. Here's a good one too. Very simple compound with 2 double bonds in a row that we look at it, okay? There's no chirocarbon. There's no chirocarbon, but the compound is chiral. Because if you build a mirror image and you try to stack them, they're not stackable. Okay. Notice on one side is flat and the other side is 3D. Okay. And that's because the structure of the 2 pi bonds back to back. That's why. Okay, now let's move on and look at more example. Fisher invented a very good way to draw the structure of a chiral compound in 2D. Okay, let's say we have these molecules. Okay, that's S. Okay, that's lactic acid. All right. Now, how do we know it's S? Now, that's 1, 2, 3, and hydrogen is 4. Okay, so if you rank them in atomic numbers, oxygen higher atomic number than the carbons, and this carbon number 2 because it has 2 oxygen bonded to it higher than just the methyl, and hydrogen is almost always the lowest one. Now, if you rotate, it's going to be 1, 2, 3. That's clockwise. However, hydrogen has to be away, but in this case, it's towards us, the viewer. So it's the reverse of what it looks like. Clockwise, actually counterclockwise. That's why this is S. Okay, now how do we do that in 2D? Okay, so now if you look at it from this angle, you will see the methyl is below. You will see that the carboxylic acid is on top. And then your hydrogen is on the right side, and then OH is on the left side. And then from there, we can translate that into a 2D structure. Okay? So vertical away. Horizontal towards viewer. Right? Okay. Okay, that's a very good one. Okay. Now, don't worry about too much about rotations unless you feel comfortable. Okay. So now if you look at this one, now remember hydrogens is towards the viewer. Vertical means away. Horizontal means towards the viewer. Okay, so when you 1, 2, 3, so that's look like clockwise, but it's actually counterclockwise. Okay. So that's why it's S. Okay. You can also do some rotations just to see how it looks. And when you rotate 90 degrees, okay, and then you turn that into hydrogen now is away. So that's 1, 2, right, 3. So now we'll talk about this later. Okay. Just make it simple. Say this one we have hydrogens. So we're going to be looking at that directions. Hydrogen on the left, OH on the right, methyl on the bottom, and CH2OH on the top. Okay, so that's good. That's the chiral carbons. Now, if we prioritize, it's going to be 1, 2, 3. So horizontal mean towards us. Okay. So if we do 1, 2, 3, that look like counterclockwise, but it's actually clockwise. Okay, so look like S, but actually R. Okay, just because hydrogens, because here we go. That's it. Keep it simple. All right. Couple more example, and with that we can do a lot. Like hydrogens towards us. So that's 1, 2, and 3. If we look at this carbon, if we look at this carbon, and 1, 2, 3, so that's look like clockwise, but it's actually reversed, so it's S. Now you switch the hydrogen to the other side. Okay, so that's become now we can erase this so we don't get confused. Okay, now if we're looking at this one, it's gonna be 1, 2, and 3. So that's look like R, but it's actually S as well. Okay, that's all we gotta do. Of course, when you do rotations, you know what you're doing. Just don't change the bond connectivity, and you'll see. Okay. In this case, I think the best is to look at each at a time, and 1, 2, 3. So that's 1, 2, 3 look like R, but it's actually S. And then we look at the other one. It's 1, 2, 3. So you do 1, 2, 3 is look like S, but it's actually R because hydrogen's towards the viewer. So you can think about this way: 1S, 1R, everything else the same, cancel out. All right. Some more example here for us to look at. Yep, forward. Okay. So when it's forward, the rotation is actually the other way. Okay. So that's 1, 2, 3. That's a good one. That's CHO. That's double bond O versus single bond O. So that's why it's first. So that's look like S, but it's actually R. Okay. Okay, diastereomers. Diastereomers are stereoisomers that are not mirror image to each other. They are geometric isomers, you see. Now, this one is trans, which is geometric, and this is cis. These two are isomers, cis-trans isomers. We call them diastereomers because they have chiral carbon. These are chiral. They're not mirror image. They're not superimposable. Okay. And you notice they have to have at least 2 chiral carbon, 2 chiral carbons. So the SR, SS, yep. Or you have the SS, the SS, the RR, these are enantiomers. Or the SR, the RS, these are enantiomers. But if you pick one that's 2S, 3R, and you compare with the SS, they are diastereomers. Okay. Yep. Or you can pick other pair as well. Here's more example of diastereomers. Again, meso compound is one that's achiral, although they have chiral carbons. Okay, it's a couple more examples for you guys to look at, and these are way that we different nomenclature, how we classify the chiral compound, like D versus L, and how we and the last great topic here is how we separate a racemic mixture. If you have SS or R, okay, or you have one S, one R. Now they are so alike that's really hard to separate them. So what you do, you combine them with a chiral reagents, and that's create, these two are enantiomers, racemic, so that's 50% of each enantiomers. When you convert them into diastereomers, they're really different, and then you can separate them. And after you separate them, you can turn them back to the original enantiomers individually. Okay, so that's useful. Racemic mixture doesn't show any chirality, optical rotations. The pure enantiomer will show the optical rotations. Okay, great. There's a few additional problem here for practice, and let's give it a try, and then we can talk about it. And here's your homework, discussion problem set. Give it a try, check the answer key, and we can discuss about them in the class. All right. Thank you, everyone, and see you in the next video.